Alright, let's go. Number 10. The Many Worlds Interpretation. In 1955, a Princeton graduate student named Hugh Everett III was not trying to reinvent reality. He was trying to solve a bookkeeping problem in quantum mechanics, how to apply the Schrödinger equation to an observer measuring their own universe without invoking a mysterious external collapse every time someone looked at something. Standard quantum theory says a particle exists in superposition, multiple possible states at once, until measurement forces it to collapse into a single outcome. The cat is alive and dead until you open the box. One reality wins. The rest simply vanish, unexplained. Everett's math refused to let them vanish. His doctoral thesis, published as Relative State Formulation of Quantum Mechanics in Reviews of Modern Physics, Volume 29, in July 1957, showed that if you never add a collapse by hand, if you just let the wave function evolve the way the equation says it should, every outcome keeps existing. The observer doesn't see one result. The observer splits, one copy per outcome. Each copy convinced it saw the only result there is. Bohr's Copenhagen school dismissed it. Wheeler, Everett's own advisor, tried to soften the language before publication and still saw it largely ignored for over a decade. The hidden variables camp proposed a deeper deterministic layer beneath quantum randomness, ruled out by Bell test experiments and their descendants, which have now closed the same loophole under more than 60 years of scrutiny. Objective collapse models added new physical mechanisms to force a single outcome, none detected, none required by the math. Everett needed nothing extra. He needed you to accept that extra was never real. If Everett is right, there is no moment in your life when only one thing happened. Every choice you almost made, you did make. Somewhere, some version of you is not watching this video right now. If reality branches every time a decision is made, how many of you are currently deciding whether that sentence is true? The math doesn't split cleanly by human choices, but the deeper mechanism raises the same question about literally everything else. Number 9. Eternal inflation's bubble universes. In the early 1980s, physicist Alan Guth at MIT was trying to fix a specific flaw in Big Bang cosmology, why the universe looks so flat and so uniform in every direction when nothing should have had time to smooth it out. His answer was inflation, a burst of exponential expansion in the first fraction of a second. The standard picture had inflation as a one-time event. It happened. It stopped. The universe settled into the slower expansion we observe today. One universe, one inflationary episode. Done. Andrei Linde, then at the Lebedev Institute, showed in the mid-1980s that inflation doesn't have to stop everywhere at once. In quantum field theory, some regions keep inflating forever, while others decay out of it, including ours. Linde's 1986 paper Eternally Existing Self-Reproducing Chaotic Inflationary Universe, published in Physics Letters B, demonstrated that once inflation starts, it becomes statistically impossible to stop in every location simultaneously. Regions that stop inflating become bubble universes. Pocket cosmoses like our own, embedded in an eternally inflating background that never runs out of room to make more. Critics propose that the eternally inflating background itself must have had a beginning, addressed but not resolved by the Borde-Guth-Vilenkin theorem of 2003, which shows any universe with average expansion cannot be past eternal, only pushing the mystery further back. Others hoped quantum gravity effects at the Planck scale would shut the mechanism down. No consistent version has done so yet. Somewhere outside the boundary of everything you can ever observe, by this model, new universes are being born right now, at a rate that never ends. Our bubble had a beginning. Did the process that made it? Every one of those bubbles, if they exist, plays by its own rulebook. Number 8. The Level 2 Multiverse. In the early 2000s, physicist Max Tegmark at MIT was trying to bring order to the growing zoo of multiverse proposals scattered across cosmology papers, so researchers could stop arguing past each other about what multiverse even meant. The working assumption in most of physics is that the constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant, are fixed. One set of numbers, built into the one universe we can measure. Tegmark's classification laid out in his 2003 Scientific American article Parallel Universes and expanded in a 2004 paper for the Science and Ultimate Reality volume proposed a second tier sitting on top of eternal inflation's bubbles, regions so causally separated from each other that the physical constants themselves can differ from bubble to bubble. Not just the arrangement of matter inside them. This means gravity could be measurably stronger 3 bubbles over. Electrons could be heavier. Entire bubbles could contain no stable atoms at all, no chemistry, no stars, nothing resembling structure. Some physicists objected that varying constants makes the theory untestable by construction, a charge Tegmark accepted rather than denied. Arguing testability of the mechanism and testability of individual bubbles are separate questions. Others pointed out string theory's landscape of vacuum states supplies a mechanism for exactly this kind of variation, which strengthened rather than weakened the proposal. The laws you've spent your life assuming are universal may simply be the local settlement. The particular values that happen to let atoms, chemistry, and you exist in this one region. If the constants are a matter of location rather than law, what does constant even mean anymore? Some regions, under this model, wouldn't even permit a version of you to ask the question. Number 7. Cosmic Bruises in the CMB. In 2010, Stephen Feeney at University College London, working with Matthew Johnson, Daniel Mortlock, and Hiranya Paris, was analyzing 7 years of Wilkinson microwave anisotropy probe data, not hunting for other universes, but refining standard techniques for characterizing the cosmic microwave background's temperature fluctuations. If bubble universes exist, and ours collided with a neighboring bubble sometime in the deep past. The standard eternal inflation models predict the collision would leave a specific mark, a disc-shaped region of the CMB with a subtly different temperature profile, distinguishable by its symmetric, non-random geometry. They built a search algorithm and pointed it at the sky. They found candidate disks. Their results, published as first observational tests of eternal inflation in Physical Review Letters, Volume 107, Article 071301, in August 2011, identified several regions consistent with the predicted bubble collision signature, but the statistical significance did not clear the threshold needed to claim detection. A companion paper in Physical Review D, the same year, ruled out bubble collisions across a wide range of the parameter space using the UMAP data specifically. The team was explicit that interesting patterns in noisy data are easy to overinterpret. Co-author Daniel Mortlock compared it directly to seeing a face in the static of Martian rock formations. Follow-up work using the higher resolution Planck satellite data through the following decade has not confirmed a collision signature either. The search wasn't abandoned because it failed outright. It was abandoned because the sky refused to give a clean answer either way. If our universe carries the scar of an ancient collision, it's written faintly enough that our best instruments still can't read it with certainty. Nobody has ruled it out. Nobody has ruled it in. Number 6. Boltzmann Brains. In 2002, Lisa Dyson at Stanford, working with Matthew Kleben and Leonard Susskind, was studying the long-term thermodynamic fate of a universe with a positive cosmological constant, the accepted mainstream model since dark energy's discovery 4 years earlier. Standard reasoning says an expanding universe with a cosmological constant eventually empties out into a cold near-vacuum state called de Sitter space, and stays that way essentially forever, doing nothing further of consequence. Forever turned out to be the trap. Their paper Disturbing Implications of a Cosmological Constant, published in the Journal of High Energy Physics in October 2002, showed that a near-empty de Sitter vacuum still has a non-zero temperature and can over sufficiently long timescales randomly fluctuate into any configuration, including a fully formed, momentarily conscious brain, complete with false memories of a life it never lived. Andreas Albrecht and Lorenzo Sorbo at Octavius extended the argument in a 2004 Physical Review D paper titled Can the Universe Afford Inflation?, showing that across the universe's full future, these random Boltzmann brains should vastly outnumber brains that arose the ordinary way, through billions of years of stellar and biological evolution. Cosmologists propose that de Sitter vacua decay before enough time passes for the fluctuations to add up, a fix that depends on assumptions about decay rates nobody has confirmed. Others propose new probability measures across the multiverse specifically engineered to suppress the Boltzmann brain count, criticized as reasoning backward from the answer they wanted. If the mathematics is taken at face value, a version of you reading these words by random thermal accident with no real past behind it is statistically more likely to exist than you are. How would a brain that fluctuated into existence a second ago ever know the difference? Nobody has found the flaw that makes the problem go away. Number 5. The fine-tuning escape hatch. Physicists working through the 1970s and 80s, including Fred Hoyle at Cambridge, were not trying to prove anything philosophical. Hoyle was trying to explain why carbon exists in the abundance it does, tracing the nuclear reactions inside stars step by step. Standard nuclear physics gave no particular reason for the carbon-producing reaction inside stars to be efficient. A slightly different resonance energy in the carbon-12 nucleus, and stars would barely make carbon at all. Hoyle found the resonance sitting almost exactly where it needed to be for carbon production to work. That single case turned out to be one entry in a much longer list. The cosmological constant is measured at roughly 10 to the power of negative 120 in natural units. A number of physicists, including Steven Weinberg, have called the worst prediction-to-observation mismatch in the history of physics, since a natural value would be vastly larger and would have torn any early universe apart before atoms could form. Weinberg's own 1987 paper in Physical Review Letters used exactly this reasoning to predict, in advance, that the constant would be small but non-zero. A prediction later confirmed by dark energy's discovery in 1998. Physicists proposed the constants might be forced by a deeper theory of everything that leaves no room for other values. No such theory has produced this result. Others proposed pure coincidence, statistically uncomfortable given how many independent constants would each need to land in their narrow habitable range. The multiverse offers a third option. With enough bubbles, an outlier like ours stops needing an explanation and starts being a certainty. You exist inside a universe where dozens of independent numbers each happen to land in the narrow window that permits atoms, chemistry, and stars. Either that's an extraordinary coincidence, or it isn't a coincidence at all, because somewhere. Every other combination is also being tried. If the multiverse is the reason you're allowed to exist, does that make your existence special, or does it make it inevitable and therefore meaningless? Nobody has found a version of the escape hatch that doesn't require believing in something equally unprovable. Number 4. No direct detection ever. Cosmologists building eternal inflation and level 2 multiverse models throughout the 2000s were not trying to build an unfalsifiable theory. They were following the mathematics of inflation to its logical conclusion, and discovering almost as a side effect where that conclusion led. Normal scientific theories make predictions you can go out and test. A particle at a specific energy. A signal at a specific frequency. Something a detector can eventually catch. Most multiverse models place the other universes permanently beyond our cosmic horizon. Not hidden by current technology, but separated by the geometry of an eternally expanding background, in a way no future instrument, however advanced, could ever close the gap. Philosopher of science Karl Popper's falsifiability criterion, laid out across his work from 1934 onward, is the line most commonly invoked in this exact debate, a claim that no experiment could ever disprove sits outside science by his definition, regardless of how elegant its mathematics is. Physicist George Ellis and astronomer Joe Silk co-wrote a widely cited 2014 comment piece in Nature. Scientific method, defend the integrity of physics, naming the multiverse and string landscape directly as theories drifting toward untestability. Proponents countered that the mechanism producing the multiverse, inflation itself, makes falsifiable predictions we've already confirmed, like the specific pattern of CMB fluctuations measured by Planck. Even if the individual other universes stay forever unreachable. Critics countered that confirming the mechanism isn't the same as confirming its most dramatic consequence. If a theory can never be tested against the specific claim that made it famous, is believing it still science, or is it something else wearing science's language? Nobody has proposed an experiment capable of settling this one, even in principle. Number 3. You and another branch. Physicists working within the many worlds framework through the 1970s, including DeWitt at the University of North Carolina, were not trying to unsettle anyone personally. They were trying to make Everett's mathematics rigorous enough that physicists outside Princeton would take it seriously. In ordinary experience, you make a choice, and every alternative you didn't choose simply ceases to be possible. The road not taken stays untaken. That's what a decision is supposed to mean. Under many worlds. Formalized by Bryce DeWitt's 1970 paper, Quantum Mechanics and Reality in Physics Today, every quantum-level branch point that could have gone differently, down to a single decaying atom nudging a decision, actually does go every possible way, in causally separated branches that can never again interact. DeWitt's paper and the fuller treatment in the 1973 volume The Many Worlds Interpretation of Quantum Mechanics he co-edited with Neil Graham was explicit that this isn't metaphor. If the formalism is literally true, the branching is as real as the world you're standing in right now. The preferred basis problem asked why splits happen along position and momentum lines rather than any other mathematical basis, largely resolved by decoherence theory developed by Wojciech Zurek starting in the 1980s. The deeper probability problem, why some branches should feel more likely than others when every branch equally exists, remains actively disputed, with Everettians like David Deutsch and David Wallace offering competing proofs that skeptics like Adrian Kent have directly challenged. No communication has ever been shown to cross between branches, not even in principle. Whatever happens on the other side of a split is permanently unreachable, yet under the same mathematics you're using to read this sentence. Just as real. If a version of you is living out every choice you didn't make, in what sense is the you reading this the one who's really deciding anything? The branches don't reconverge. Whatever splits, stays split. Number 2. The measure problem. Cosmologists building eternal inflation models through the 1990s and 2000s, including Alexander Vilenkin at Tufts University, were not trying to break probability itself. They were trying to answer a basic question. Given an eternally inflating multiverse, what's typical inside it? Ordinary probability requires a finite set of outcomes, or at least a well-behaved infinite one, so you can meaningfully say one thing is more likely than another. Eternal inflation produces infinitely many bubble universes, of infinitely many types, and the standard mathematical tools for comparing infinities break down the moment you try to ask which outcomes are common and which are rare. Vilenkin's work through the 2000s, including his 2007 paper Freak Observers and the Measure of the Multiverse in the Journal of High Energy Physics, showed that different, individually reasonable ways of counting infinite bubbles produce wildly different, sometimes contradictory, predictions about what a typical observer should expect to see, including predictions about whether Boltzmann Brains outnumber ordinary observers. The proper time measure produced answers dominated by runaway pathologies. The scale factor cutoff measure, developed partly by Vilenkin's collaborators, fixed some of those pathologies but introduced arbitrary choices about where exactly to cut off an infinite process. A 2010 paper by DeSimone, Guth, Lindy, Norbala, Salem, and Vilenkin in Physical Review D tested several competing measures directly against the Boltzmann brain problem and found none of them fully satisfying without additional assumptions bolted on. There is currently no agreed-upon way to calculate what you should expect to observe if you live inside an eternally inflating multiverse, which means the theory that predicts your own universe can't yet predict how typical your universe is supposed to be. If a theory can't tell you what a typical observer should see, how would you ever know if you were one? 2 decades of competing proposals later, cosmologists still can't agree on how to count to infinity correctly. Number 1. String theory's landscape. String theorists through the 1980s and 90s, including those working to unify the 5 known versions of string theory, were not trying to produce a multiverse. They were trying to find the single, unique mathematical structure that would explain all of physics from first principles, the long-sought theory of everything. The early hope was that requiring mathematical consistency alone would pin down one specific theory, with one specific set of particle masses and force strengths, matching our universe uniquely. Instead, the compactification of string theory's extraspatial dimensions turned out to allow an enormous number of geometrically distinct solutions, each one a self-consistent set of physical laws, each one just as mathematically valid as any other. Leonard Suskind's 2003 paper, The Anthropic Landscape of String Theory, posted to arXiv as HEP/0302219, named and popularized this space of solutions as the landscape, building on earlier work by Raphael Busso and Joseph Polchinski. Later estimates, developed through work by Suskind, Michael Douglas, and collaborators on flux compactifications, put the number of distinct stable vacuum states at roughly 10 to the power of 500. A number so large that comparing it to the roughly 10 to the power of 80 atoms in the observable universe barely conveys the scale. Some theorists hoped a deeper principle would eventually select one vacuum as the true one. Decades of searching have found no such principle. Others argued the sheer size of the landscape means string theory makes essentially no unique predictions at all, a criticism physicist Peter Woit pressed at length in his 2006 book Not Even Wrong. Suskind's own response embraced the landscape rather than fighting it, arguing the anthropic principle across 10 to the 500 possibilities explains fine-tuning without requiring a deeper mechanism. If string theory is correct, the specific values of gravity, the electron's mass, and every other constant that makes your body possible are not laws at all. They are one arbitrarily selected outcome, sitting among more possibilities than there are particles in everything you can see. Out of 10 to the power of 500 ways for physics to be arranged, this one produced you. Nobody can currently explain why this valley in the landscape, and not one of the others. That's the countdown. 10 theories. 10 teams of scientists who were not looking for the multiverse when they found it. They were closing out ordinary problems in inflation, string compactification, and quantum measurement, and the mathematics simply refused to stop where they expected it to. The universe is not confused about what it's doing. We are the ones staring at equations that keep producing more universes than we know how to count, or test, or ever visit. Every entry on this list sits not at some speculative fringe, but inside our most rigorously tested theories, general relativity, quantum mechanics, inflation, string theory, each one pushed hard enough that it started answering questions nobody asked. If any of them are right, the version of reality you're sitting in right now is one page in a book with no cover and no back. If you want to see more videos like this, click the video on screen now.